Yeah, so a TV color simulator. One project we found, I don't know, 10 years ago we found a paper on the the power spectrum of a candle in still air, in light breeze and heavy breeze. Who would do that for research and publish it? Well, it turns out there's big money in it because you want your LED candle simulator to be statistically reasonable. And it turns out that after doing a whole pile of fast Fourier transforms and looking at a whole bunch of data, it turns out that a candle is insignificantly different than a white noise generator passed through a low-pass filter. And the cutoff frequency of the low-pass filter is determined by how hard the breeze is. So you can make quite an adequate candle simulator with 20 or 30 lines of code on microcontroller. Lecture hasn't actually started yet. I'm just blabbing about final projects.
It would be also useful if you're designing a church.
Wait a minute, wait. Which is, the TV or the candle?
The candle. You open the doors.
Oh, so wouldn't it be fun to make a candle that's breeze sensitive with a little thermistor? You take a thermistor, you know what a thermistor is, right? Negative temperature coefficient resistor, has a high negative temperature coefficient. Well, if you put enough current through them to self-heat, so you jack them up to their rated wattage, and then blow on them, they cool down, and their resistance changes. And so you can use them in a voltage divider and detect the resistance change and get an idea of the velocity of air going over them. And so you could make such a device. The problem is that the resistor has to have a very small heat capacity so that it responds quickly like a flame. Now you could do that with a surface mount resistor hanging in air. It's a tough sell. Other possibility is make a vibration sensor. So when you blow on the thing, the vibration sensor picks up the vibration. And that's actually, you could do that for 50 cents. So anyway, like I said, strange final project ideas. But now, are there any questions with Lab 2? Let me restate that because I put the wrong specifications in the lab, you don't actually have to auto-scale the frequency. You all heard that last time, yes? If you set the prescaler to divide by 8. Let's see, I saw one strange error in lab. What was it? I've lost it. Okay, let's go back to Lab 3. Any questions on Lab 3? I think last time I left off with talking about FM synthesis and the need for speed. So the tone we're going to make, and I wanted to bring along my laptop today and so I could play some of these tones for you, some of these sounds, these FM sounds, but I couldn't make the thing find the network this morning. So I obviously have to do a little bit of work on my laptop. So I'll just simulate it with my voice. Anyway, the sample we're going to produce, the output waveform we're going to produce for a given musical note is going to be some amplitude times the sine of 2 pi f naught. And I'm just writing this up again so I can point at it because I already wrote it up last time. Plus some amplitude FM times some FM depth FM times sine of 2 pi frequency of the FM modulation, where amplitude is going to be given by an exponential rise and an exponential fall of form equals A naught e to the minus t fall, t over t fall, times 1 minus e to the minus t over tau rise, where tau rise is the time constant on the rise and tau fall is the time constant on the fall. And amp FM is going to be given by a simple exponential some A0 e to the minus t over tau FM. I think I wrote that all down last time. So we can't afford, as I said last time, we can't afford to calculate all these exponentials and sines and cosines on every time step. So we're going to have to strip away as much of the mathematical overhead as we can and make something faster. Any questions about this? All right, well, let's start with generating an exponential. So we have some t equals 0 here. Well, in the context that you're going to be doing this work, there's going to be some t equals 0, which is really going to be the time that you need to strike a note, that a note has to be sounded. All right, so it won't be 0, but we'll for simplicity here, we'll call it t equals 0. And then, as you all know from some class long ago and far away, or maybe not so far away, this equation can be written as some dx dt is equal to minus kx with some a naught at x equals 0, where this height then is a naught. And what we want to do is we want to convert this into a rapidly computable form in C. Because if we can calculate the differential equation quickly, then we can calculate the exponential fall quickly, without having to look up without having to do an exp operation on every time step, which is too slow. So we're going to generate the exponential by solving the differential equation. Could you do it with a lookup table? So I haven't tried that. Yes, it probably will work. So you pick some time, and then you scale all the times to that time constant, and then you interpolate the time. So you have to. So the trick here is that you have to properly index into the table, and doing it one linear interpolation. And I think the way I'm going to suggest is faster than that, but I'll be happy to see. We could do a bake-off and see whose is faster. I think it would work. I'm going to Taylor expand this, in fact. That's how we're going to solve it. And we're going to do the cheesiest possible Taylor expansion called an Euler solution. Euler. You remember Euler? If you have to guess, you say Gauss or Euler, if it's mathematical. All right, so we can rewrite this. If we want to solve this on a computer, we need to turn continuous time into discrete time. The discrete time being the sample frequency that we're going to be synthesizing at. And we're going to rewrite this differential equation with an index, xn, n being a time index. So this is the nth sample, this is the n plus first sample in time, over delta t, where delta t is equal to 1 over the sample frequency, fs, which is going to be probably about 8 kilohertz to start with, is equal to minus k xn. And we always know xn because, after all, we get to choose the first one. And so we can then calculate the next one by solving this equation. And then on the next time step, we plug that back into xn and one step forward at a time. So we're going to solve this, obviously, as xn plus 1 is equal to xn minus delta tk times xn. Now, we're going to choose to make, for efficiency, this is for efficiency, we're going to choose to make delta tk equal to 2 to the minus p. And when we do that, then this equation becomes x to the n plus 1 is equal to x to the n minus x to the n shifted by p. Shifted right by p. That's pretty fast. So for every time step to calculate an exponential, you have to do one shift and one subtract. P is what you choose to be the time constant. It's related to k, which is what, 1 over the time constant or something. It's related to k, but it is some rate at which the system decays. What this says, however, is that you can only set the time for a constant delta t, and you will be having a constant delta t because your sample frequency will be constant. For a constant delta t, you can only set k in factors of 2. It's either it's going to have a time constant of decay of 1 second, or 2 seconds, or 4 seconds, or 8 seconds, but not 10 or 7. And you ask yourself, is that good enough? Well, maybe. It's certainly almost good enough because, after all, everything of interest in your nervous system is logarithmic. It's all ratios that matter. And so powers of 2 kind of make sense. And it's really fast. So that gives us a decay for this curve. For the rise and fall, we need 1 minus exponential. So by analogy, there's going to be some other variable, yn plus 1, which is going to be given by a naught minus yn minus yn shifted by some q, which is the equivalent rising time constant. And then the amplitude, here you'll actually have to do a multiply. The amplitude is going to be given by xn plus 1 times yn plus 1. There you will actually have to do a multiply. We want to arrange it so that it's an integer multiply only. Any questions? So we're going to use integer arithmetic, but we really need fractions because we want these functions to change smoothly and slowly. So what we're going to do is we're going to say that an int, a 16-bit int, in our minds, in our heads, we're going to pretend that an int is really an integer piece and a fraction piece with a binary point between bits 7 and 8. And so we'll refer to this as 8-8 fixed point. So anything to the right is a fraction. Anything to the left is an integer part. Is this familiar notation, people? And so you can ask yourself, for 2's complement addition, if we write a number like this rather than as just one long integer, does 2's complement addition work? I see a lot of nothing like this. So what's the consensus? Does it work? Yeah, it works. There's no change. It's just in how you think about the result. Now, multiply, though, is a little different. Because if you multiply two integers together, two 16-bit integers, then you're going to come up with a... Let me start erasing some stuff here. Any questions before I erase this stuff? Differential equation stuff. So if we multiply two 16s together, of course we get a 32-bit result. And in our thinking, the binary point is there. Now for an 8-8 fixed point, the binary point is going to be in the center of the 16-bit field. So we have a 32 result. Where's the binary point exactly? It's at 16. Oh, so what do we do? Well, that means out of the result we need to take this byte and this byte, throw away the overflow, and throw away the underflow. So what you should do to do this correctly is to cast both of these to longs, do the multiply, and then shift the long 16 bits to the right and cast back to int. Alright, so if this is A and B, let's see, you should cast A to a long times, that's not right, cast A to a long, cast B to a long, then shift to the right 16, and then cast back to int. $16. 8. You're quite right. Thank you. But that's fairly slow because then you have to do a 32-bit multiply. It's a 32, and it's just a mess, and it's fairly slow. So what seems to work? What we're going to do here, this is not mathematically correct, folks. But what works, it's really cheesy, is that A times B is approximately equal to A shifted to the right 8 times B shifted to the right 8. So what have we done? We've totally ignored the fractional piece and just multiplied the integers. I see some of you look a little queasy, a little nauseated at the thought. Now, the reason we can get away with this is that in the end, at the bottom of this process, we're going to be putting the number out into an 8-bit pulse width modulator. That is to say, the total precision that we have at the end of the process is 8 bits. And so we can afford to throw away the low order digits because they almost don't matter. Almost.
Why are we using floating point?
It's not floating point. Fixed point? Oh! So that we can keep enough accuracy that these calculations make sense. Because you're going to be shifting to the right by 8. If it was an 8-bit number you were using, you'd be subtracting 0 every time, and that would not be good.
Does this hinge on the fact that you're using such a low sample rate that you're not even going to perceive the differences in precision?
It hinges on the fact that 256 voltage levels is pretty good. Now, I got to tell you that these various approximations do have a tendency, unless you're really careful with the round off, which I wasn't, they tend to make a very low background whine about 25 dBs below full volume. Now, that's a factor of 100. Let's see, make sure we're right in the right. It's a factor, it's 10 log 256. So let's make sure we're in the right units. So it's a 40 volume, 40 voltage dBs. That's not enough so that you cannot hear it, but it's enough that if you turn up the volume and plug your ears, it sounds okay.
Did you do A/B testing to see like if losing precision would actually be audible? Then
I suppose you could. I didn't bother because I wanted to go for absolute speed, so I kept everything as simple as possible. I'm not saying this is the best, but it sure is fast. So this requires only an integer multiply rather than a 32 multiply, so it's quite a bit faster. We have to do a bunch of those so that it's worthwhile having it fast. So we're keeping the 16 bits so we can generate smooth exponentials. The 16 bits allows us to generate smooth exponentials, but in the end, when we're calculating an amplitude, we only need the high order 8 bits because that's all we've got for the output. So, any questions? So we take the nice, you could write this in MATLAB in one line, you write this in one line, you calculate it out. It executes almost in real time on a 3 gigahertz dual core machine. And it's really easy. It's lines of code. It puts out a sound file, you play it. What I'm going to be asking you to do on the microcontroller is somewhat different. At every time step, at every sample time, every 1/8000th of a second, you're going to produce the next sample that's necessary of the signal, output it to the pulse width modulator, and then get ready to calculate the next sample. Again, questions? You don't have to, as specified in the lab, I'm suggesting that you use FM modulation, but you don't have to. You can use additive synthesis, Fourier synthesis, with, let's say, 3 or 5 Fourier components, each one of which has its own decay time or not. It depends on how you want to set it up. And then the determining equations will be slightly different. But you'll basically still have to calculate some exponentials, and you'll have to calculate, therefore, the amplitude and some sine waves to make a signal. So either way you want to do it, it's going to come out to something like the same amount of arithmetic. If you decide to use additive, each FM synthesis is approximately the same complexity as a 2 Fourier component additive synthesis. And so if you used 4 Fourier components, we'll count that as 2 voices in terms of speed, the product for grading. It's very quiet. That can mean one of several things. Often it means I went too fast. Oh, I'm going to get to that. You mean how you actually do the sign? I haven't talked about how you actually calculate the signs yet. Is that what you're talking about? So additive synthesis, you mean like what is additive synthesis? Okay. So additive synthesis is what you learned in some class on orthonormal functions. I don't know, complex analysis, signals. I don't know what it's called here. Where you say that any periodic function can be written as the sum of a sine wave series with some A0 plus A1 sine 2 pi F1, where F1 is now the fundamental, plus A2 sine, plus a phase 1, plus sine 2 pi F2 plus phase 2 plus dot dot dot, as many terms as you want to carry out. So is it hot in here, or is my thermostat turned up too much? Just my thermostat's up. Internal thermostat. So that should be really familiar. So this is some output now using the same terms as over there. So your output at every time step is going to be the Fourier sum of some series, where you get to choose the phases and the amplitudes to do whatever synthesis you want to do. Now it turns out humans are not awfully phase sensitive. So it's mainly the amplitudes that matter. And you'll almost always, for audio, have A0 equal to 0 because you can't hear DC. Unless it's really loud. Like a blast wave. You know, some overpressure wave. So that's sort of the additive synthesis scheme. What else did I put in there? Another one was Carpel strong. And what was the fourth one in the lab? Oh, I have the lab here. FM additive, or, oh, I just said 3. Okay. Now, Carpel strong is a much different kind of algorithm. It is an approximation of the wave equation on a string. And what we want to know is, for a string that has some sort of arbitrary waveform on it, what it's going to sound like. And you say, oh no, we're going to have to solve a second order partial differential equation, and it's going to be ungodly slow because we have to at least break the string into parts that are small enough that the waveform covers several parts. Otherwise, we're going to get aliasing. So we're limited in the pulse size, in the minimum width of the pulse size, which means we have to have lots and lots of sections. We have to do a lot of calculations. But Carpel and Strong noticed something, and that is, let's say you have a traveling wave like this, a nice pulse on a linear lossless string. You know, it's like, you know, consider the temperature distribution in a spherical chicken. They don't really exist, but it's nice to think about them. Linear lossless string. What happens to the shape of this pulse as it propagates? Nothing. Oh, it's like a delay line. And so the first thing you do is you say a string is just a delay line in which at some time after you put a voltage in, you get a voltage out at some delay in total number of clock pulses. And then there's a -1 at the boundary. If this is a hard boundary, remember when the wave comes back, it's reflected 180 degrees out of phase. Remember that from Fields and Waves or EM or whatever. Okay, so it's reflected. Then we have a shift register going back this way, a -1. And now we have a lossless string simulator. Now, if we want to add a little bit of loss, let's say that at any step along here, as we go from across this boundary into the next delay line cell, we multiply by some number near 1, some attenuation factor, which is like 0.9995. So the energy coming out of that section is a little bit smaller than the energy going into the section. The way we're going to model that is we're just going to shrink the waveform by a small amount at every delay element step all the way along. And that simulates a lossy linear string. Right? Now, here's the key trick. The key trick is that all of those operations, multiplying by -1, multiplying by a constant near 1, and delay, are all linear operators. Right? Yes? That means you can commute the order of them. Right? Okay. Oh, well, a -1 and a -1, you commute those together and you get 1. And so we can replace this by a single delay line whose length is twice as long. If this is L, this has to be 2L. We replace the -1 times -1 by 1, which is to say we don't do anything. We replace the loss with one loss element, which is 1 multiply, and then we feed it back into the input. Wow, that's really easy. That's a ring buffer in C. That's a ring buffer and 1 multiply. But it's even better than that. Because what they noticed is that if you look at how the harmonics on a string die out, at short times you get a high second harmonic, a high third harmonic, a fairly low first harmonic, but that after a very short time, or after any time, the energy in a harmonic dies out as if this string was being fed through a low pass filter with a Bode plot that looks like this, with an amplitude response that looks like this. And so if we just put a simple RC filter in this feedback loop, we get something that sounds very, very much like a plucked string. And the loss model that they used in the original Carpel-Strong algorithm was embarrassingly easy. You have a delay of 1 sample. You feed it through. You add these two together and divide by 2. What? It's what?
I accidentally plucked the string.
What? I'm sorry.
I accidentally plucked the string.
Oh. It sounds like a string, doesn't it? You want to turn it up and play it?
Sure. I don't know if it'll be that loud, but...
Oh, well, you want to come up and plug it in? Then it'll be loud. Hold it up. It sounds like a plucked string. And so for the cost of a loss element and a delay and an add and a shift by 2 to normalize, you get something that is very string-like. If you load this at t equals 0, at the time you pluck the string, if you load this with white noise, you get something that sounds like a fingernail hitting a steel string. Very broad bandwidth. White noise is equivalent to a very broadband noise. If you filter the white noise, before you load it into the shift register at time t equals 0, and then let it circulate, it sounds more like you hit it with the soft part of your thumb. You get a softer sound. So Carpel-Strong gives you a way specifically of making good string sounds, although people have added permutations of this. You put an output filter here, you put a high pass here, and a low pass here, and you make sure that the cutoff frequencies are the same for these high pass and low pass, and you make the cutoff in the hundreds of hertz, and it sounds like a horn. The reason for that is that the bell of a horn tends to pass high frequencies better than low frequencies. So the low frequencies get bounced back down the length of the horn and recirculate, and the high energy comes out the end of the horn. I have a whole book written about this by Julius Smith, but you can get the whole book online. Just Google up Julius O. Smith. It's a cool website. They do things like the sort of forefront of research now is three-dimensional instruments. Can we completely model a violin? Can we completely model a drum, including the bottom of the kettle and the resonances in the stick? You know, it's all this physical modeling stuff that's very, very interesting. But that's a third method. It's quite different. It is a physical simulation, whereas the FM scheme is completely ad hoc. It makes no particular physical sense. It just sounds good. The Fourier synthesis at least makes physical sense. You're simulating the mathematical structure of the sound, but you're not simulating the physics. Here you're actually simulating the physics. Questions? Was that enough on that? There's enough on different methods?
So how will we determine the length of air?
Say again?
How will we determine the length of air?
Oh, the length. Well, you tune it. The longer it is, the lower the pitch. Because the longer it takes a circulating, so you can calculate out that it at 8 kilohertz sample rate, middle C is going to require 33 and a half, a shift register of length 33 and a half. Say, oh my, half a shift register step? Oh dear. So what do? A phase shifter. That's right. You use a phase shifter. You use a phase shifter, an all-pass filter, with a maximum phase shift of 1 sample, and then you can tune fractional samples by mixing the phase shifted and the unphase shifted version to get any exact frequency out that you need. And I think the examples online do that on the DSP page. The DSP page is linked off of Lab 3. Might want to start reading that. So there was a question last time, how do you generate a random number? And that's important here because quite often a little burst of white noise really makes a difference in the synthesis of a sound. So when you, for instance, if you're simulating voice, T, that initial transient is almost is broadband white noise. It's almost unfiltered, and the reason it's almost unfiltered is it comes from right here at my lips, and so it's not going through any filters. It's right up the front. Whereas the sound coming out from my vocal cords is being filtered through a very complicated bandpass filter, which is my throat and nose and you know, eustachian tubes and position of my tongue and my teeth and my lips and all that. So if you were going to simulate an E sound or a T sound, you need a burst of noise. So if we now plot T and F here, time and frequency, this is called a spectrogram. Spectrogram where the amplitude is encoded by the color, the density of the chalk, then you'll see that the sound T is going to be a burst of white noise followed by about 3 harmonics whose position is determined by the size of my throat and the position of my tongue. Those are called formants, but that without the sound, you just have E. And in many musical instruments, the first sound you hear is a burst of noise. Let's say if you open the valve on a device like a tuba that takes a long time to build up, takes a long time for the resonance to build up, you can get a little burst of noise when the valve opens. So you can make something that sounds more realistic by putting just a little bit of noise mixed in at certain points. So it's nice to have a fast random number generator. You're going to need a random number generator in any case for this lab to drive the Markov process. So we need a fast random number generator that's pretty good. And I don't like rand built into C, and I'm not sure why. I just don't trust it. So what I prefer, and again, it's more of a gut feeling than anything I know for sure. It's just that a lot of people screw up rand when they implement it. So you could implement your own. What I like to do though is use what's called a linear feedback shift register. We're going to have a bit shifter. In this case, we're going to go for 32 bits. It's going to shift to the left. Bit 0, bit 31, and bit 27 are going to be the important bits we need to look at. And we're going to feed back through an XOR. We're going to feed back through an XOR bits 30, 31, and 27. Sorry, oh, excuse me, 30 and 27. And if you do that, and the exact bits you feed back are important, you get out a series of ones and zeros whose pattern only repeats after 2 to the 32 time steps. And there is no serial correlation between bits. In other words, it's a random number generator. So for instance, you could shift this 7 times, run it 7 times, and then read the low order 7 bits here and get a number which is completely uncorrelated with the number 7 shifts before.
What did you write that?
7 times. Shift it 7 times and you get a brand new 7-bit number out. And so if I want to generate random numbers, I just put something like that in main. I just put it in main and let it run at whatever speed main is running. And whenever I need a new random number, I just read the lower 7 bits of it. And now that's not C code yet, that's hardware. It's really easy to implement on FPGA too. Yeah.
So what do you initialize this register?
Anything but 0. That would be the seed. 0 is boring. So I'll write out the C code for that next time, or you can do it yourself. I'll write it out next time. But this is quick and efficient. It requires 2 32-bit shifts. Well, sorry, 1 32-bit shift per time step, and 1 XOR, and a couple of bit mask operations to pull out 30 and 27. And you can find, if you look up linear feedback shift register any place, you can find out the appropriate bits for any length of register that you want. You don't like 32 bits? 32 bits will repeat after what? 2 times 10 to the 9th cycles. So if you run it at a megahertz, it's going to repeat every 40 minutes or so. That's probably good enough. You might be able to get away with 16 bits for this operation, for this particular application. If you wanted to have it a repeat time longer than the age of the universe at a megahertz, increase it to 127 bits. I wrote a 127-bit random number generator for a very demanding simulation. And then I calculated, well, I'm running the simulation at 50. I'm generating 6 numbers at 50 megahertz. How long will it take to repeat? Never. Effectively, never. Entropy will kill the galaxy before it repeats. That's a good definition of never. So, we got a couple of minutes. Let's talk about final projects. The the recurring theme, final projects. A good quiz question, if the number of people went down a little bit, it's good today. If a good quiz question would be, write down your top 3 final project ideas in 3 minutes. So you better have that at the tip of your pencil. Anybody have any ideas for final projects? Jeremy? Oh yeah, please, stand up and talk about it for a moment.
So I'm not going to work on this, but someone else might be interested in doing it. So there's a guy who works for Cornell at the Lake Placid Research Center, and they basically take maple syrup from trees and turn it into like syrup that you put on pancakes and stuff. So he needs a control system that monitors this big steam kettle thing with a thermocouple and opens a valve every certain amount of time based on the temperature that the sap from the tree gets to, and allows the maple syrup to flow out and lets the new raw sap flow in, and then do some monitoring over time and have like a readout and a control mechanism and things like that. And they would pay for you to go up to the Lake Placid Research Center and install it in May or something if you're interested. So if anyone wants to do that, let me know and I can bring you in touch with them.
Industrial application with big servos and interesting motors, interesting sensors. And this is, I mean, the vats are like this big. Any other comments on final projects? Any ideas? Automatic bartender. Okay. For ethical reasons, I said no projectile projects, nothing that can be construed as a weapon. I also have to say that you can't do anything that suggests alcohol. Now, that being said, I mean, I've had 2 people build breathalyzers, and they had to figure out a way to test it that did not require them drinking alcohol in lab. What they do on their own time is their own time. But there was one project called the Big Red Juice Mixer that was slash dotted. It was slashed and brought. I got a message at 10 o'clock in the morning saying, "We thought Cornell was under a denial of service attack, but it was just your web page. Congratulations." So they built this dispenser that could dispense 4 or 5 different liquids with gram precision. Had servo valves and a mass and a weighing device under the cup, and they could dispense quite accurately. And they were demoing it with unsweetened Kool-Aid. So it's about 10 o'clock at night. We've been in it. It was really hot. It was before the lab was redone. We were boiling in there. My TA, who was kind of goofy anyway, they show this thing. It fills up this glass with dark liquid, and he grabs this and says, "What is this stuff?" And they said, "It's Kool-Aid." He goes, slurp, and freezes. He says, "Chris, are you okay?" And behind me I hear, "Maybe we should have put the sugar in it." So it's like pH 1 tartaric acid, right? And I said, Chris, are you okay? Can you breathe? He said, "Yeah, I can breathe. I think it feels like I barfed in my own mouth. Oh my God." And to tell you how sad it was, I was rolling on the floor laughing. It was a long day. Let's get out of here.